All right, welcome to section 5.3. We're looking at independence and the multiplication rule right now. And last section in 5.2, we were focused on the word or, and or meant addition. We're going to find in just a second that the key word and is going to mean multiplication. So I'm going to write and at the top. That's going to be our key word for multiplication. Okay. All right, so before we talk about multiplication, we have to talk about events being independent or dependent. When we're talking about or, we're talking about mutually exclusive or disjoint, which has to do with common outcomes. Now we're talking about independence and dependence. And two events are independent if the occurrence of event E in a probability experiment does not affect the probability of event F. So when we talk about independence and dependence, we're talking about probability. All right, mutually exclusive is common outcomes or not common outcomes. Independence, dependence has to occur or has to deal with the probability. All right, and then likewise, two events are dependent if the occurrence of event E affects the probability of event F. All right, so let's look at some examples. Are the following independent or dependent events? So again, that means we're going to be focused on the probability. So think probability in this case. Okay, so suppose you draw a card from a standard 52 card deck of cards and then roll a die. Are the events draw a heart and roll an even number, independent or dependent? Okay, so let's break this down again. Let's look at the probability of drawing a heart out of a deck of cards. Well, that's 1 out of 4 suits. You can also think of that as 13 out of 52 cards because there's 13 hearts. So every slice, it's going to be a fourth. And then rolling an even number, that probability is 2, 4, or 6. Those are the outcomes I mean. So it's going to be 3, 6, or half of probability. Okay, so if we were to draw a card and we got, a heart, would that affect the probability of rolling an even number? No, it absolutely would have no effect on either one. So these probabilities would remain the same. They're not going to change whether or not we draw a heart or we don't draw a heart, whether or not we roll an even number or not roll an even number. They're going to stay the same. So these are considered independent. All right, let's look at our next example. Suppose you draw a card from a deck of cards and you draw a king. Without putting that card back, that's going to be important. Without putting that card back. So we started with 52 cards. If we don't put it back, now we have 51 cards. So without putting the card back, you draw a second card and get a king. Are the events a king on the first draw and a king on the second draw independent or dependent? Okay, well, let's write it out. So the probability of getting a king on the first okay, how many kings are in a deck? How many cards? Good. So we have a 1 in 13 chance of getting a king. Okay, and now let's look at let's getting a king on the second draw. All right, well, it depends. First of all, how many cards are left? 51 cards. All right, so our sample space is going down to 51 because we took a card away. And it depends. If we got a king on the first draw, how many kings are left? 3. That's perfect. All right, and if we did not get a king on the first draw, how many kings are left? 4. And we still only have 51 cards in our deck. So the second probability is affected by the first event. Because if we get a king, it's one probability. If we did not draw a king on the first draw, it's a different probability. So in this case, the probabilities are affected. So these are dependent events. Okay, here we go. All right, part C. Suppose two 40-year-old women who live in the United States are randomly selected. Always a great term to focus in on. Are the events woman 1 survives the year and woman 2 survives the year independent or dependent? So if someone is randomly selected and they happen to live in New York and they survive, and another woman is randomly selected and they live in Washington and she survives, are those events independent? Are their probabilities affected if the woman in New York survives? Does that affect the probability that the woman in Washington survives? And it doesn't, right? They are unrelated, so the probabilities stay the same. It's independent. And now let's look at this next example. Let's say, suppose two 40-year-old women live in the same apartment complex. Are the events woman 1 survives the year and woman 2 survives the year independent or dependent? Well, it's no longer random, right? Because these women live in the same apartment complex. So actually the probability that they're surviving affects each other. For instance, let's say there's a carbon monoxide leak in their apartment and the first woman dies. Well, that's going to affect the probability of the second woman surviving, because the carbon monoxide is going to go to the other woman's house and then she's going to die too. So the event the woman 1 survives the year, well, if she doesn't survive, if she dies for whatever reason, that could put woman 2 at risk. So that's going to affect the probability. So in this case, because it's not random, because they're related now, it's dependent. Okay. So I mentioned it at the beginning of this section, the difference between independence and mutually exclusive. A lot of students get those two terms confused. They think they're the same thing. But we have to remember that independence, we're talking about probability and events affecting one another. And mutually exclusive just means common outcomes. And does one imply the other? Absolutely not. They're two separate things. So for instance, let's consider the events drawing a 7 and drawing a heart. And we'll just do like a single draw. So on a single draw, or we could do a replacement. So we have the same sample space each time, or sample size. So single draw, or we can replace the card. And then that way our sample space is just 52. So the probability of getting a 7 is 1 out of 13, 4 7s out of 52. And the probability of drawing a heart is 1/4. So if we're doing a single draw, these probabilities aren't going to be affected by one another. If we draw a 7 on the single draw and put the card back, that shouldn't affect it at all if we get a heart next time. So these two events, drawing a 7 and drawing a heart, are independent when replacing the card. But they're not mutually exclusive. Okay, so again, I'm just doing this example because mutually exclusive and independence or dependence and not mutually exclusive, they all have separate definitions. Independence does not imply disjoint. Okay, so kind of our PSA, our public service announcement. let's go on to our regularly scheduled program. So we're going to be flipping a coin twice, and we want to know the probability of flipping 2 tails. Okay, and these are independent events. I have this little note, is flipping tails once independent of flipping tails again? Absolutely not. Every time we flip a coin, it's independent of whatever we got before. Okay, so if we flip a coin twice, we're going to get heads or tails, heads or tails. So let's do our sample space. And I'll write it like this. We could get 2 heads. We could get 2 tails when we flip a coin twice. We can get a head and then a tail. We can get a tail, then a head. Okay, so we have 4 things in our sample space. And we want to know the probability of getting 2 tails. Well, we can just count up, the amount of outcomes in event E. To find the probability. And we can count up the amount of outcomes in our sample space, and it would be a 4th. Let's try to develop a formula for this section. So event E is T and T, right? 2 tails. That's really probability we get the tails on the first flip. I'm going to write it out. And then we get tails on the second flip. Ooh. And I just said the word and. Okay. So probability of getting tails on the first flip, I'm just going to break it down like this, is 1/2. And the probability of getting tails on the second flip, just by itself, again, is 1/2. All right, so we're just theorizing right now. So if we have 1/2 and 1/2, what operation could we use to get to a 4th? Because we know this is the answer. We know 1/4 is the answer. And here we have 1/2 and a half. And how are these two related to get a 4th? And they're related by multiplication. If we multiply 1/2 by 1/2, we get a 4th. All right, so this is telling us something about our multiplication rule. So let's write it up. So we were developing a formula, and now we have the multiplication rule for independent events. All right, so for independent events, E and F, we have the following. So the probability of E and F is just multiplication, probability of E times the probability of F. And again, this is just for your independent events. And then we can extend this too, just like we did with the addition rule. So if we had something like probability of E and F and G, we would just multiply 3 things. Probability of E times the probability of F times the probability of G. All right, so let's look at an example. So a manufacturer of exercise equipment knows that 10% of their products are effective. Lovely. They also know that only 30% of their customers will actually use the equipment in the first year after it's purchased. If there is a 1-year warranty on the equipment, what proportion of customers will actually make a valid warranty claim? Okay, so I'm just going to break down what it means to be a valid warranty claim. It has to be within the first year, and they actually have to use it. Because if they don't use it, they won't know what's effective, or defective. So a valid claim, warranty claim, means it's used in the first year and they have to discover it's defective. And then they'll get their warranty. Okay, so what proportion of customers, proportion, that's another way of saying probability. So that's kind of a new way to say probability. What proportion of customers, proportion, probability, they're both percentages, will actually make a valid warranty claim. So what proportion or probability has a valid warranty? Well, that's if they used in the first year and effective. And these are both, if we look, and that's our multiplication rule, right? And these are two events. Used in the first year is your first event. Defective is your second event. And these are mutually exclusive because before you use it, whether or not you decide to use your equipment has nothing to do with the fact that it's defective. You wouldn't know it's defective till after you decide to use it and you open the box and realize it doesn't work. So the probabilities are not going to be affected by these. These are independent. So we can use our rule we just established, so probability that it's used in first year or used in 1 year, and is multiplication. And then it's the probability it's defective. All right, and we're given these probabilities. The probability that it's used in the first year is that 30%. And then the probability that it's defective is that 10%. All right, so only 3% of their customers are going to be making a valid warranty claim. That's not very high. So why fix a product? Why fix a bad product if you're only going to have to replace 3% of them? All right, and so the moral of the story there's lots of morals in this story, but what I want you guys to really focus on and remember is and is multiplication. And is multiplication. Let's look at another example. So we're going back to that survival rate that we were just looking at. So the probability that a randomly selected female aged 60 years old will survive the year is 99.186%. What's the probability that two randomly selected 60-year-olds will survive the year? All right, so randomly selected, we talked about that on the first page. That means these are independent events. That's a D, independent events. Okay, so let's break this down. What is the probability that two randomly selected females will survive? Okay, so we want to know the probability, essentially, that both survive. Let's write that out into words so we can see what rule to use. That means the first survives. The first woman survives. And the second woman survive. So both means and. So we know we're going to have to use our multiplication rule. I ran out of room, sorry about that. Okay, survives. First survives and the second survives. Okay, so according to our multiplication rule, these are independent events, the first woman surviving and the second woman surviving. They're independent events because they're randomly selected. So because it's the probability of two independent events with the word and, we're going to use our multiplication rule. And is multiplication. And we're given both of these probabilities. So it's, where is it? 99.186. So it's 0.99186 times the same. But rather than writing that product twice, the same product twice, we have a shortcut way of writing it. We can use an exponent. So let's use an exponent instead. And then we'll put that into our calculator. And we'll get our solution for that. All right, so that's from our calculator. I always like to give the answer in the same format it was given to us in the problem, which was a percentage. So I would actually write this as 98.343%. All right. Okay. Let's look at the same type of example. So we're still dealing with 60-year-old females in surviving the year. And now we want to know the probability of 4 of these women surviving the year. All right, so you can probably figure this out on your own if you want to pause it and then play when you think you have the solution. But 4 women surviving, that's like the first and the second and the third and the fourth surviving. And they're independent because they're randomly selected. So we can use our multiplication rule. I'm just writing first, but it stands for first surviving. And all these probabilities are the same. So rather than writing out the same probability 4 times and multiplying it, we can write it out once. Where is it? Right there. And raise it to the 4th power. That's also a little bit easier to write into your calculator and make that a little bit more of 4th power. There you go. All right, and then we get your solution. So notice that probability is getting smaller and smaller the more women we're adding. And that's because when you multiply something less than 1, it makes the product smaller. And it's also a stronger condition, right? If we want this one to survive, and this one to survive, and this one to survive, and this one to survive, we're becoming stricter. So our probability is going down. It's easier for 1 woman to survive than all 4 to survive. And we see that reflected in our solution. Okay. We are looking at now at least probabilities. At least probabilities, we're going to be using our complement to help us solve at least probabilities. All right, at least probabilities, like if something is at least 4, we know it's 4 and above. So at least 4 would be like 4, 5, 6, 7, 8, 9 to infinity. And we use the symbol greater than or equal to 4. So we solve using the complement. And we'll see how we use that in just a second. Okay, so let's write out our event, and let's use this greater than or equal to 4. So let's say we had values of our variable. It could be like how many pairs of shoes you own or something like that. All right, so here's a sample space. And if someone is greater than or equal to 4, so at least 4, it's this event, right? So someone could have 4, 5, 6, 7, 8, or 9 pairs of shoes if it's at least 4. Okay? All right, so the sample space is between 0 and 9 kinds of shoes. So at least for the complement then, whatever's left over, we see is 0, 1, 2, and 3. And so we can think of this as less than 4. And that's the complement. We could think of it like this, which is the opposite of greater than or equal to, strictly less than 4. We can also think of that as less than or equal to 3. All right, so these are all things we're going to be using. All right, so how we could do this really quick, if we wanted to look at the probability of greater than or equal to 4, we could look at 1 minus the probability of the complement. And we just said the complement was less than or equal to 3. Okay? All right. So here we go. Let's look at this first example. The probability that a randomly selected female again survives the year is that same number. What is the probability that at least, keyword, 1 of 500 randomly selected females will die during the course of the year? Let's break this one down. All right, so the probability of at least 1 dying during the course of the year. If you think of this, this is the probability. So 1 out of 500 that 1 woman could die, or 2 women could die, or 3, or 4, or 5. And we would have to calculate all of these probabilities using the addition rule all the way up to 500. And that's horrible, right? No one wants to do that. So rather, we're going to use the complement. All right, so the opposite of at least 1. So similar to what we did up here, except now instead of 1, or 4, we have 1. So the probability of greater than or equal to 1 is going to be less than or equal to 0, or 0, right? So let's do a little side work. All right, I'm going to do a little side work. I'm going to write out 1 through 500. Or actually, these are all the options of how many women could die. We have 0, 1 woman could die. So no women could die, 1 woman could die, 2, 3, all the way up to 500. And this is at least 1. So that's the event we're trying to find. We're trying to find greater than or equal to 1. That's going to be our solution, and we're going to use the complement. So what's left over? Well, less than 1 is left over, or 0. So the complement of at least 1, the complement of at least 1 is 0. All right, let's go back to that. Okay. So we're going to use our complement rule, because this is horrible, to calculate all 500 probabilities. So 1 minus the complement of at least 1 is 0 dying. Okay, so that's the first step. After we do this, we can't really calculate the probability of 0 of anything, right? Because there's no multiplication rule. So we have to translate from none to all. So out of 5 women, if 0 die, that means 500 survive. So our first step is to write it out in terms of the complement, and then we go from none and we translate it to all. Okay, so that's kind of a tricky step. Okay, so let's continue on. So 500 surviving, that means the first and the second and the third and the fourth, all the way up to 500 survive. So that's like the example 5 we just did. But instead of 4 women surviving, 500 survive. So we're going to raise that probability to the 500th power. All right, and so the probability that at least one woman out of 500 die is 0.98320. All right, so even though the survival rate is high for a 6-year-old woman to survive the year, if we look at a group of 500 women, the probability that at least one's going to die, even though the probability of survival is high, it's 98%. Oh, so there you go. All right, let's look at a similar example. You guys could do this one on your own. So you guys can push pause and then come back when you think you have the solution. All right, so Christmas lights are designed with a series circuits. This means that one light bulb burns out, the entire string goes black. That's old school. Suppose that the lights are designed so that the probability a bulb will last 2 years is 0.995. That's pretty good. So what's the, the success or failure of a bulb is independent, is always important, of the success or failures of other bulbs. This is just telling us that we can use our multiplication rule. So what's the probability that a string of 100 lights, all 100, will last 2 years? And it seems like it would be good because the probability that it will, a single bulb, is 0.995. All right, so this is really saying what's the probability your string of lights will last 2 years? Because if one goes out, all go out. So I hope it's high. Okay, so the probability that 100 will last, or all. So again, that's really the first and the second and the third. Okay, so that keyword and means multiply. So the probability of the first times the probability of the second. I'll write all that out. Times all the way up to the 100th. And the probability is the same for all of them. So we're going to multiply 0.995 100 times, so we can just raise it to the 100th power. And then when we do that, our probability kind of plummets, sadly. So we have a D chance, a 60.6% chance of our light lasting for 2 years. All right. Well, there you go. So kind of on the flip side, what's the probability that at least one bulb will burn out in 2 years? So this is really the probability that our string of lights will last 2 years. Keyword, at least. So that's telling us, that's a keyword. When we see at least, we have to think complement. Whoops. So 1 minus the probability of the complement. Okay, and let me write this out a little bit more thoroughly, because we want to get everything correct. So at least one burns out. Because remember, we have to go from none to all. So none burn out. So out of 100, because our string is 100 lights, none burning out means all will last. So 100 will last. All right, and that's what we calculated in part A. So we already did that work. So this is going to be 1 minus 0.606. So what's the probability that one light bulb will burn out and our string of lights will be useless? That's 0.394. Too high for me.